The new module introduced in X7 Release 3 is the wind module designed for generating wind loads. Before exploring the functionality of the module, let's start with a brief historical overview. The SVG module provides the ability to automatically generate the snow and wind load on typical structures according to standards since the introduction of AXISVM X4 in 2017. In 2021, the X6 version introduced the CFD module, allowing the import of wind loads from fluid dynamic simulations performed in external programs. With this module, wind loads can now be generated for any structure, but it requires prior CFD analysis in external, typically hard-to-use software. The new wind module provides digital wind tunnel simulation integrated into the AXISVM workflow and complex handling of loads with the conversion of results into wind loads. In the following slides, I will briefly summarize the purpose of the new wind module. With increasingly complex architectural shapes becoming more common and cost-effective design becoming increasingly important, the standard approach does not adequately account for wind loads on these complex structures. Wind tunnel testing is one possible method, but it is very expensive and time-consuming, making it viable only for very large projects. Computational fluid dynamics, also known as CFD analysis, essentially functions as a digital wind tunnel test, offering a much more economical and quicker solution. The wind module enables such analysis to be conducted easily within the AXISVM environment. There is no need for external, often hard-to-handle software. Instead, all input parameters and analysis details can be easily specified directly within the familiar user interface, allowing for a seamless computation process. We can easily visualize the results of the analysis, such as pressures or wind speeds, in a variety of eye-catching ways. For us, structural engineers, the most important result is the external pressure factor on the structure. Based on this, the wind module generates the loads for structural design. Another advantage of the module is that it allows for the examination not only of individual structures, but also of the interaction between multiple structures. The fluid dynamic calculations are based on OpenFOAM, a widely used, free and open source computational engine developed for solving general continuum mechanics problems. The module is designed to determine external pressure factors, and we recommend its use for determining internal pressures only in simpler cases. Steady-state flow is considered, which means phenomena such as Kármán vortex shedding and resulting fatigue loads are not taken into account. During the calculation, the structures under investigation are treated as rigid bodies, meaning their displacements do not influence the pressure factors and aeroelastic instability losses cannot be examined. All surfaces are assumed to have the same roughness. The terrain around the structures is assumed to be flat. In the following, I will demonstrate the use of the new wind module using a practical example. First, I will provide an overview of the workflow, followed by a detailed explanation of each step. We start with a model created for structural analysis. This model needs to be prepared for wind tunnel testing. For example, load panels can be defined to enclose structures if necessary, or if we want to examine the effects of surrounding structures, we can model them with non-load-bearing load panels. Once the model preparation is complete, we can also define the wind loads and wind directions on the loads tab. After defining the loads, the parameters of the analysis can be set on the wind tunnel tab, and then the calculation can be initiated. After the calculation, the results can be visualized and analyzed in various ways on the wind tunnel tab. First, let's focus on preparing the model for analysis. In this scenario, I am modeling a closed grid shell structure. I am considering the cladding between the structure's beams using load panels. If I wanted to examine only the grid without the panels, that could also be done. The module is primarily designed to determine external pressure factors, so it is advisable to cover openings with load panels in the case of complex interior structures. However, simple interior buildings such as a hangar or unenclosed truss structures can be analyzed without issues. Next to the structure, there is a building whose impact I want to consider in the simulation. The outline of the building has already been drawn. If we want to consider the effect of the surrounding structures, but do not intend to perform structural calculations on them later, we can use non-load-bearing load panels. After defining the load panels, select them and then choose the option for non-load-bearing load panels from their settings. The simulation can be run on a selected submodel where only the displayed details are involved in the calculation. Thus, for example, I can perform a simulation on this single model with and without considering the neighboring building's impact. It's advisable to ignore details on the structure that are not relevant from the perspective of the wind load. Many small details can unnecessarily slow down the calculation and may even cause convergence issues. Currently, there are no details that I want to ignore, but for a model with many details, this is a crucial step. After preparing the model, the wind directions and wind profiles have to be defined. In the load cases and load groups window, multiple load cases can be created. Each load case is formed within a load group named CFD. Only this load group can exist, and all load cases are established within it, mutually exclusive. I modified the names of the load cases for easier differentiation later. In the simulated wind window, the wind directions and wind profiles have to be defined for the previously created load cases. The load case name is visible at the top of the window. Wind directions to be considered in the calculation can be defined in two ways. It is possible to specify an angle range within which an arbitrary number of wind directions are evenly distributed. Additionally, there is the possibility to create any number of custom wind directions. The created wind directions appear in the list called directions and are displayed in the visualization figure shown below. When specifying the wind profile, we have the option to choose between standard and custom wind profiles. It is advisable to use standard profiles whenever possible. Custom profiles should be used only if you intend to utilize a standard wind profile not available in the program, or precise individual measurements are available. Terrain category and the terrain level can be defined. Additionally, air properties and numerous other parameters can be modified if necessary. For CFD-A, I used terrain category 0 and set the terrain level to 0 meters. The initial negative value was specified because the lower frame beams of my structure are below the model 0 level, but I don't want to consider this in the simulation. After pressing the OK button, the load cases corresponding to the wind directions have been created. Similarly, I define a few wind directions for the CFD-B load case, but here I use terrain category 3. After creating the simulated wind loads, the analysis can be initiated. To start the analysis, click on the Wind Tunnel tab. By clicking on the Run Wind Tunnel Simulation button, the analysis settings can be accessed. The simulation can be run for one or more selected load cases. The analysis parameters can be specified on a simple or a detailed interface. If the geometry is not significantly detailed, typically comprising of surfaces, the simple input mode is usually sufficient. In this case, the mesh density can be adjusted using a slider, and the number of iterations and the stopping criterion can be specified. The stopping criterion relates to the pressure error threshold. In case of the detailed parameter specification, 3 additional tabs will open, where the analysis settings can be customized in detail. On the wind tunnel model tab, you can adjust the size of the model space and the modeling settings of the structural elements. In the wind flow model space panel, you can control the dimensions of the cuboid representing the wind tunnel relative to the height of the structure marked as h. A too small model space can result in false effects in the analysis, while a too large model space unnecessarily slows it down. The default values are set according to literature recommendations. For low height and wide structures, ensure that the projected area of the structure on the inlet side rectangle does not exceed 3%. By changing the scale, the required mesh density can be significantly reduced. However, the calculation remains accurate only for structures independent of Reynolds number. In general, it is advisable to stick to a 1:1 scale ratio. On the Structure Modeling Options panel, you can regulate the geometric parameters of the structural model placed into the wind tunnel. Under the exported elements, you can toggle the elements comprising the wind tunnel model on and off. Every element, including load panels, must have a thickness, which can be specified in the thickness field. The intersect connecting element setting eliminates the difficult to mesh regions at the intersections of elements. In the cross-section panel, you can choose to model cross-sections with their axial shape without rounding or with their enclosing rectangles. With simplifications, the mesh density can be reduced by orders of magnitude, which can greatly accelerate the calculation. On the ribbed slabs panel, you can choose whether to export such slabs with ribs or without. As mentioned during the modeling, before initiating the analysis, you can also control which parts of the structure are included in the wind tunnel by selecting details. It is advisable to simplify the model by selecting the appropriate details, considering only the elements that actually influence the wind load. Wind loads will be generated only to the elements placed into the wind tunnel. On the Mesh tab, you can control how the meshing is generated for the simulation, as well as the resolution at which the generated wind load is applied to the structure. During meshing, the program initially generates a base mesh that does not yet take into account the structure. On the 3D block mesh panel, the mesh size setting allows for adjusting the fineness of this base mesh. In the next steps, the program refines and adjusts this base mesh using mesh refinements and alignments to adapt it to the structure's model. To understand the parameters of mesh refinement, we need to introduce the concept of levels. The cells of the base mesh are at level 0. When we halve a cell in every 8 dimensions, 8 small cells are created. This is called level 1. With further halving, we obtain 64 cells at level 2 and so on. In the following, I will illustrate the effect of parameters on a simple model. The model is a cube with a side length of 5 meters. On the following slides, I will show a cross-section of the wind tunnel. The first slider allows us to specify the mesh density level to be applied within the bounding cuboid of the structure. A minimum and the maximum value can be set. The program refines the mesh in 2 steps. It uses the minimum level on the outer part of the bounding cuboid, while it uses the maximum level on the inner part. This is the mesh we get with level 1 setting, and the mesh we get with minimum 2 and maximum 4 refinement. The number of cells between level slider controls the transition in mesh refinement. Between level changes, at least this many layers of cells are used at a given refinement level. This is the mesh with the setting on 1, and this is it set on 3. When specifying surface mesh refinement, the meshes that come into contact with the surface of the structure's model undergo further refinement. Minimum and maximum values can be provided. Setting this parameter to 3 while keeping the others at the minimum results this mesh. It is advisable to use this setting on curved surfaces and thin profiles where the geometry changes rapidly. Near the surfaces of the structure, the gradient of the velocity field is very high. With boundary layers, the mesh can be further refined by inserting additional layers around the surfaces to better account for this phenomenon. The effect of this setting can be seen in the figure. By default, this feature is disabled. It is not recommended to use it for curved surfaces. In this case, I am applying the following meshing settings. From the results of the simulation, loads usable for structural design are generated onto the structure. The model assigns a so-called wind load mesh to the structural elements, and the generated load is distributed on this mesh. For surfaces, this load mesh consists of triangles, while for line elements it consists of segments. The average side lengths of these triangles or the lengths of the segments can be adjusted using this setting. On the Solution Control tab, in addition to the default K-epsilon turbulence model, 3 additional models can be selected. Furthermore, besides the default stopping criteria based on pressure error threshold, additional stopping criteria can also be specified. By clicking the OK button, the simulation can be initiated. Only the selected load cases will participate in the calculation. The first step is generating the mesh. Upon completion of meshing, without interrupting the calculation, the program displays the wind tunnel in a separate window with the generated mesh. In general, it is advisable to start the analysis with a coarser mesh and check the results in this preview window. If you find the mesh to be too coarse, the calculation can be stopped and the mesh can be further refined. During the analysis, we can monitor the aerodynamic forces acting on the structure in the local system of the wind tunnel. In the residuals panel, we can track the change of the applied stopping criteria. If the calculation has converged, the results and the mesh of the model can be displayed on the wind tunnel tab. The load cases to be displayed can be selected from the drop-down menu. There are 4 types of result visualization methods available. When displaying the structure envelope, you can choose between showing the wing pressure acting on the structure or displaying the pressure coefficient. In the section planes display mode, pressure values and wind velocities can be displayed in any arbitrary section within the model space. For wind velocities, options include velocity components and resultant velocity. Multiple sections can be displayed simultaneously. In scanner display mode, the parallel cutting planes aligned with the tunnel sides can be interactively shifted, as well as the planes of custom sections. The same results can be displayed as with the section planes. There is also an option to play and export animations. In the streamlines display mode, vertical and horizontal series of streamlines can be created. The streamlines to be displayed can be selected using checkboxes. The position, number, starting point and end point of the streamlines can be modified. Any number of streamline series can be displayed simultaneously. The animation displaying the streamlines can be played and exported. In the Display Parameters window, you can adjust the load cases, display modes, and the components of the displayed results. Additionally, you can choose to display the wind tunnel mesh. The first option displays all meshes, while the other options allow you to specify specific parts of the mesh for easier overview. The wind tunnel option shows only the mesh generated for the wind tunnel's perimeter. The model surface mesh displays the mesh on the structure surface. With the section plane option, you can display the mesh in arbitrary sections or scans. Finally, the WindFlow model space toggle displays the bounding box of the digital wind tunnel. The final results are the static loads reduced to the structure. These loads can be seen on any tab if the load display is enabled. The question may arise how the wind module relates to standards. The module includes wind profiles according to Eurocode and SIA. However, none of these standards provide detailed guidance on conducting CFD simulation. CFD simulations should be used in conjunction with building regulations and standards, not as a replacement for them. According to the Eurocode, structural design should be based on validated and verified numerical CFD simulations. Our validation examples and descriptions serve as a useful resource for finding numerical settings aligned with the standards. It's important to note that expertise both in CFD modeling and standard guidelines is necessary for conducting CFD simulations for wind load calculations. This presentation served as a brief and superficial overview of the new wind module. For more detailed information, our wind guide and user's manual provides comprehensive descriptions. Additionally, verification examples and sample models are available. We are planning to create more detailed practical example models in the future. These models would be paired with their explanations of the applied settings and their rationale either in written or video format. If there is sufficient demand, we could also consider hosting a more detailed webinar with the developers.